Hey scholars, it's good to be back with you. And today I'd like to talk to you about finding roots. Now some of you may notice, this is my second video on finding roots. I shot one yesterday that had an error in it. And I want to thank viewer Mateos Bielecki, I hope I have your name right, for finding that error and bringing it to my attention. So rather than try to fix it in some clumsy way on YouTube, I thought it'd be better to just try again. I'll shoot a fresh video and it'll go better this way. So, finding roots. I want to start by saying, what is a root? Why would you want to find one? And then we're going to go to a numerical method on how to find roots and do some number crunching. If you want to skip ahead to the number crunching part right now, absolutely fine with me. Okay, if you're still with me, let's talk about what a root is and why you'd want to find one. So, root of an equation is when you set an equation equal to 0 and solve for the value of x, or whatever your variable is, that makes this equal to 0. Now it gets called a couple of things. Root is one of the most popular names for it. It also gets called a zero. You'll see that sometimes. In fact, in MATLAB, one of the root finding algorithms is called F0, to find the zero of a function. So root or zero, either one of them is fine. They mean the same thing. So that's what it is. Why would you care? Well, the puzzle has two pieces in it. The first is the nature of mathematics. The nature of mathematics is that we use mathematics to describe the world around us. We can write equations on pieces of paper or on our computers that tell us things we want to know. It might be about some product or some process. It may be financial, whatever. But the equation means something that we care about. That's part one of the puzzle. Part two of the puzzle is that all equations, or almost all of them, can be manipulated so that you get something equals 0. In fact, if you start and you've got some stuff equals some other stuff, remember that equal sign means what's on this side and what's on this side are the same thing. Subtract this from both sides, push it over there, and you've got something equals 0. So with algebraic manipulation, just about any equation can be written out as some function, like f, equals 0. So when you're trying to solve this, you're finding a root. And just about any algebraic equation can be written this way. I say just about. I'm having problems thinking of one that isn't. There's got to be one somewhere. But almost all the ones you'll ever see can be written out as f of x equals 0. Solve that, you're finding a root. So that's why you'd want to do it. Right? So that's the first step along the path here. Now, I need an equation, so I wrote this out. This doesn't have any physical meaning as far as I know. I made it up. And I made it up for a very specific reason. It only has one real root. It's got two imaginary roots. It's got three roots because it's third order. But it's only got one real root, and it is, let me use my cheat sheet here. I'll call that x star maybe, is 4.361. Okay? So right about there is where the function crosses 0. So let's start by looking at this graphically. Get my red marker here. Right there, the green line here, the green curve, that's what happens when you plot this function. Now I sketched this out. I'll show you the computer version a little later, but this is close enough. This is about what it looks like. And where f of x equals 0, right there, that's where the root is. And that number right there, that's x equal 4.361. That's the root. That's how to find it on a plot. All right. Now those of us who have ever been to, I don't know, probably junior high school, have learned analytical ways of finding roots. If you have a second order polynomial, a quadratic equation, there's the quadratic formula. You take the parameters, the coefficients in front of the x's, and you ram them through the quadratic formula and you get the two roots. Okay. There is a cubic formula, it's about that long. There is a quartic formula, it's about that long. There is no closed form solution for polynomials of higher order than 4, and nobody ever uses the cubic or quartic formula. They're just too clumsy. In fact, almost nobody outside of schools, classrooms, ever finds roots of functions analytically anymore. When I say analytically, I mean pushing symbols around on a piece of paper, like the quadratic formula. That's an analytic solution. You manipulate equations on a piece of paper and you finally get x equals something. And that's how you solve functions analytically. Well, it's been a long time since anybody did much of that. You'll see analytic solutions occasionally in derivations and things, and of course in textbooks where we're trying to teach people algebra. But in practice, roots are almost always found numerically. We almost always take an equation like this one, push it into a computer, and tell the computer to give us the answer, which is of course how I did this. Here's my cheat sheet over here that I've got stuck to my board. I did this in a program called MathCAD, and I'll show you all the calculations here in a minute. I'll put them on the screen for you. That's how I did it. I'm not about to try to do that analytically. There's just no value in it. So if numerically is the way we're going to solve all these things, wouldn't it be good if we know how to do that? Let's try it. Now, there are many, many numerical solution algorithms for finding roots, more than I could ever describe. I'm going to show you the very simplest one, the easiest one to work with. Others work a little bit differently, but in principle, they behave the same way. Behind the screen, in software, it's acting a little differently, but the interface to you, the part you see, is going to look pretty much like this. So here's what I'm going to show you. It's something called the bisection algorithm, and it also gets called binary search. That's the other name for it. Okay, those two names for the same thing. So here's what we're going to do. We're going to actually erase my board here. Erase this little bit. Give me some room. Take a range of numbers. Get that out of my way. Take a range of numbers and assume that the root lies in between the beginning and end of that range. So I'm going to start there, and I'm going to say x0 equals 0. So far, so good. And I'm going to say there x1 equals 6. I'm going to assume that the root lies between those two. Now, how will I know? Well, let's see. If it's negative on one side and positive on the other, it has to have gone through 0. So if I say f of x0 times f of x1, I'll get out of your way here in a second. If that's less than 0, that means one of those two had to be negative. If they're both negative, that product will be positive. If they're both positive, that product will be positive. Only if you've crossed through the horizontal axis will the product of those two be negative. Now, how do I know that my root lies in between those two? Well, I don't. In practice, what you do is you just set the limits so far apart, you know it's got to go through 0 there somewhere. And what I did is I just plotted it. But if I just plotted it on my computer, why don't we always just plot them? Why bother with all this stuff? Shouldn't we just plot them and look? The problem is to do a plot, you have to do many, many function evaluations. Right? And the game with solvers is you're trying to find the answer in as few evaluations as possible, calculating numbers like that and that as few times as possible. Now for this, it doesn't matter. It runs so fast, as soon as I hit enter, the answer's going to pop up. We have those algorithms for the situations in which calculating that or calculating that is not cheap. It's expensive. It takes a long time, and computer time costs money. So we want efficient algorithms to find roots. That's what this is about. So when you look at root finding algorithms, they're trying to give you an answer in as few calculations as possible, because sometimes those calculations are lengthy and expensive. Okay, so I've got a range here from 0 to 6. So I'm going to divide that range in half. Okay, and delta x is going to be half the range. So delta x is x1. Try that again, there we go. x1 minus x0 over 2, and here it's 3. Okay, so I'm going to figure out f of x0 plus delta x, and f of x1. And I'm going to multiply this one times that one and this one times that one and see which one's negative. Well, I don't have to do that here. I have a picture. I can look and see, well, here it hasn't crossed the axis. So I know the root doesn't lie here. Here it has crossed the axis. So now I know, instead of the range being from 0 to 6, now I know it's somewhere between 3 and 6. I just cut the range in half. I erased it here with binary search. I just cut the range in half. So after iteration 1, my range went from x0 equals 0, x1 equals 6. Now I have x0 equals 3, x1 equals 6. My range just went down by half. And I'm going to just keep doing this, cutting my range in half every time. And so the way you do this is you make a table, right? And I'm going to draw the table out here in a second. But you'll be able to see every row is going to be an iteration, and at the end here we'll have a range, x0 and x1. And all we know is that the root lies between x0 and x1. We don't know where it is in there, only that it's in there, right? So I'm going to erase my board and start working on this table, okay? Cool, the whiteboard elf showed up. Well, here we go. Here's our numbers. We started it with x0 equals 0, x1 equals 6, delta x equals 3, because that's half the range there. And then here's these two products. Well, I'm looking for the one that's negative. Well, that one's positive, that one's negative. That means after my starting point here, I know, like we saw in the picture, that the answer lies between the midpoint and the end. So for the next iteration, x0 equals 3, x1 equals 6. Now this is going to be 1.5. And let me just write these numbers down here, and then I'll show you the computer, the printout here in a second. So this one is minus 115.625. And this is 397.75. Okay, well, this one's positive, that one's negative. Okay, so x0 is unchanged. x1 is changed. I've cut the range down from the other end. So now I know the answer is between 3 and 4.5. And just to remind you, I'll call it x star there for the answer, is 4.361. We'll be able to check our calculations here, because if I ever wind up with a range that doesn't have that in between the beginning and end, doesn't include that, I know I've messed up somewhere. So I'll do one more iteration here. I guess I'll write this out. This is, let's see, that's going to be 0.75. The range right now is 384.766 and minus 71.182. Okay, and again, I know that one's positive. I don't need that one anymore. One other thing to note before I go to the screen here is that, see how these numbers are starting to get smaller? Yeah, no, on average, they're starting to trend smaller. Well, as I get closer and closer to the root, the function should get closer and closer to 0. So as that range gets smaller and smaller and smaller, and each end of that range gets closer and closer to the root, these numbers should trend smaller. They ought to get pretty small as I get close to the root. Well, let's see if that happens. Rather than sit here and try to have me write all this down, let's just go ahead and I'm going to take this sheet and put it on the screen for you. Okay, you can see it on the screen here. And I've done 8 iterations. The first couple of iterations are the ones that I wrote on the board. And you can see as you go all the way down to iteration 8, a couple of things are happening. Delta x gets smaller and smaller and smaller. This is good, because all we know is that the root lies somewhere in the range. We know that it's in between x0 and x1. So delta x, which is half the distance between x0 and x1, should trend to 0, and it does. It starts out at 3, and by iteration 8, it's 023. Another thing we should notice is that the product of the functions at the beginning and middle of the range, and then the middle and the end of the range, those numbers ought to trend smaller, and they do. They started out at hundreds or thousands, and by the time I get to iteration 8, One of them is 1.04 and the other one's minus 0.026. So they're getting smaller. I must be getting near to the root. And if you look in the bottom right of the sheet here, you can see that x0 is 4.359 and x1 is now 4.383. That's awfully close to 4.361, which is the right answer. And one of the nice parts about this algorithm is you can run it as many iterations as you want. If you want to go more than 8, if you want to go dozens or maybe even hundreds to get more and more and more precision, to know more and more and more accurately the answer, you can do that. Now, the only thing to remember is that we don't know where inside the range the root lies, only that it does lie within the range. So as you run more and more iterations, x0 and x1 are going to get closer and closer and closer together. Because of that, your uncertainty goes down. As long as a root lies in between x0 and x1, you are going to find it. So there's a numerical root finding algorithm. Now, is this the most efficient one out there? Absolutely not. Is this the simplest one out there? Man, it has to be awfully close. It's hard to imagine one much simpler than this that still works. So it has the features that an algorithm should have. It's iterative, so you can get as precise an answer as you want. It converges on the answer, and it does so very reliably or robustly. And it gives you a good estimate of what your error is. Remember, you know what x0 and x1 are, so you know that the root lives in between there somewhere. So as you tighten up the range of x1 and x0, you have a very good estimate of what the error is. It can't be any more than that distance between x1 and x0. So we've talked about roots, talked about analytical solutions, we've gone over a numerical solution. Hope this helps, and we'll talk to you next time.